Today we're going to start a new unit focused around exponential, logistic, and logarithmic functions. We won't focus on logarithmic today, but we will get there soon. So it's going to be important to keep in mind what these three images look like and what the characteristics of these graphs are, what their functions are. For an exponential function, we are using a base function of y equals 2 to the x. For logistic, we don't yet have a function for this. And then for logarithmic, we were using the log base 2 of x. But just like the exponential, that base 2 doesn't have to be base 2. It could be base e, it could be base 3. But those are the base functions that we're going to use moving forward. Exponential functions are going to take this form of f of x equals a times b to the x. The key characteristic here is that x is in the exponent location. The variable is in the exponent. This is going to be our base form for exponential functions moving forward. To define a few things here, a is our initial value. And one thing about this initial value is this must be a non-zero value. So a can equal anything other than 0. It could be a positive number, it could be a negative number. B is going to be our base, and that base must be a positive not equal to 1. So we could have a fractional base there, we could have a decimal base there. A lot of times we work with integer bases greater than 1, but we could also have a base between 0 and 1, as long as it's positive, not equal to 0. We're going to continue with exponential here. So we've got this initial value that's non-zero, we've got a base that's positive, not equal to 1. We're going to extend this and talk about exponential growth versus decay. Exponential growth is often used in population, maybe the population of bacteria, the population of some other living being. Sometimes we also talk about exponential growth of finance or something along those lines. We'll also discuss decay. Decay, a lot of times you hear of radioactive decay, you hear of half-life. That's where exponential decay is going to come in. So the two functions that we're looking at here, one would be an exponential growth model, and one would be an exponential decay model. The big difference here in terms of the examples is that this exponential growth will be something like the quantity of 2 to the x, whereas the decay model will be something along the lines of 2 to the negative x. We likely won't use 2 to the negative x as much as we will use 1/2 to the x. If we recall, 2 to a negative first power should be the same as 1 over 2 to the first power, or 1/2. So as we look at that negative x in the exponent, we're actually going to treat that on the 2 to the negative first as a 1/2 power. If we go back to our knowledge of transformations, that negative that's multiplied times the x would create a reflection about the y-axis, which we can see graphically here. If we're talking about growth and decay, we can also see that the model on the left is going to grow. As x increases, the y is going to increase. The model on the right, as x increases, the further right we move, the y decreases and approaches a value of 0. For both of these, we have a horizontal asymptote of y equals 0. And for both of these, we also have a y-intercept of the point 0, 1. To find a y-intercept, we're going to insert a x value of 0 and determine what would be left. If we have 2 to the 0 or 1/2 to the 0, either way we're going to yield a 1. We're now going to work with a specific function. For this function, which we're going to define as f of x equals 2 times the quantity 4 to the x, we are going to graph this function. We're going to talk about any key features and label several points on this graph. I'm going to do this by using a chart to label some values here. Let's first plug in some negatives. If we plug in a negative 2, f of negative 2 would be equivalent to 2 times 4 to the negative second. It's important to note here order of operations. Should we multiply the 2 times 4, or should we do the 4 to the negative second power first? We should do a 4 to the negative second 4 to the negative second is the same as 1 over 4 squared, which is 1 over 16 times 2 will yield a 1/8. If we plug in a negative 1, f of negative 1 will give us 2 times 4 to the negative first, or 1/4 times 2, which will yield a 1/2. If I plug in a 0, I will get 4 to the 0 times 2. 4 to the 0 is 1 times 2 is 2, and that's going to be my y-intercept. I can plug in a value like 1. 4 to the first is 1 times 2 is 8. I get f of 1 to be equal to 8. Something to note here, if I insert a 3/2 into my x, I'll have 2 times 4 to the 3/2 power. Well, how should I look at this? I'm going to look at it as 4 to the 1/2 power cubed. 4 to the 1/2 is the same thing as the square root of 4. So now I'll have 2 times 2 to the 3rd power. 2 to the 3rd is 8 times 2 will give me a 16. When I insert 3/2, I get out a 16. I'm going to insert a few last numbers here. If I insert a 2, 4 to the 2nd times 2 will yield 32. If I insert a 3, 4 to the 3rd is 64 times 2 is 128. Finally, if I insert a 4, 4 to the 4th times 2 will yield a 512. Now, what pattern should we recognize here? If my x value increases by 1, what is the multiplier on my y value? If my x value increases by 1, I'm going to increase my y value by a multiplier of 4. We actually have to skip over that 3/2 because we're increasing our x value by 1 to get that multiplier of 4. We should see that in the base. We can plot these points. We're going to get a shape that looks exponential. We're going to get a horizontal asymptote of y equals 0. We're going to get a y-intercept of 0, 2. And I could plot the rest of those points, generally speaking, from there. We're going to begin to introduce this letter E here. E is called the natural constant. It has a lot of properties that are very useful in calculus as well as computations involving growth rates. E is going to be formally defined as the limit as x approaches infinity of the quantity 1 plus 1 over x to the x power. I'll leave that out there for you to explore further. For us, E is going to be approximately 2.718281828. That's what we'll get on our TI calculators, but that makes this number look as if it is repeating and therefore rational. It is not. If we do another 3 decimals, we would see that we do not repeat, and this number will be an irrational number, cannot be expressed as a fraction, non-terminating, non-repeating decimal. Let's keep that number in our back pocket as we will use E a lot with exponential, logistic, and logarithmic functions. The last thing we're going to discuss today in more detail is the logistic function. So we've seen this in the past, where a logistic function is going to have a horizontal asymptote that bounds it on the bottom. A lot of times that horizontal asymptote is y equals 0. The logistic function will also have a horizontal asymptote that bounds the graph on the top. That top is going to be called the carrying capacity. A logistic function does not increase limitlessly like a normal exponential function does. It's bounded by that carrying capacity. This is an important note because most populations will not increase forever at an exponential rate. There will be some cap, and that's what this carrying capacity is. What we haven't defined in the past is what the equation of this is. F of x is going to equal c over 1 plus a times b to the x. We've seen that a times b to the x with an exponential function. Now that's in the denominator added to a 1, and we've got this value of c in the numerator. A couple notes here. A, b, and c are all positive values. B needs to be less than 1. C is what we are going to call the limit to growth. I also like the term there of carrying capacity. It is the value that our function cannot go above. What I'm going to ask you to do now is I'm going to ask you to graph the following three functions. F of x equals 6 times the quantity 1/3 to the x, g of x, which equals 1/2 4 to the x, and finally h of x, which equals 32 divided by 1 plus 3 times 1/2 to the x power, all in the denominator. For these three functions, I'd like you to graph. I'd like you to plot 5 points. Included in those 5 points must be the y-intercept. I'd also like you to show and state any horizontal asymptotes. For this, you can use your grapher, but you also should be able to plug in x values, create a chart, find the corresponding y value, and plot those points that will give you an image of this graph.